Başlayalım. Özgür.
Okay. Good evening, everybody. It's a great pleasure for me to introduce you, my dear friend and a great researcher this evening to you. Our speaker is Hakan Türeci. He's from Princeton University of USA, and he's going to give us a very interesting subject, very modern subject that we are all anxious to hear about. It's about machine learning with quantum dynamical systems. Before his talk, I would like to take this opportunity to thank him personally and also on behalf of all qubit community, because this talk is a unique talk in the history of qubit meetings. For the first time, we want to access broader audience, especially to younger audience, to give a taste of modern quantum optics, quantum information, modern quantum research. And thanks to Hakan, we have the perfect person to give you this talk to you. So thank to him for this great support to our, hopefully will be a tradition, a series of talks on evening lectures. Hakan is an associate professor currently in the Department of Electrical Engineering at Princeton University. So before Princeton, he received his undergraduate and master's degree in Bilkent University and received his PhD from Yale University in 2003. He performed his postdoctoral studies at Yale and ETH Zurich, and also joined ETH Zurich as an assistant professor in physics. After that, he moved to Princeton in 2010, and he contributed in many branches of quantum physics involving nanoquantum dynamics, statistical mechanics, classical and quantum many-body collective systems, and his current focus is on superconducting circuits as well as linear and nonlinear optical systems. So thank you very much, Hakan, for being with us, and we look forward to listening. Welcome.
Thank you, Özgür. And good evening, everyone. Thank you all for tuning in. I'm delighted to be part of this conference and have been enjoying the talks in my waking hours here. I believe this conference is a great service to the physics and the burgeoning quantum information science community in Turkey. So I wholeheartedly support it. The added personal benefit is that I'm seeing a number of good old friends in the list of participants. I'd like to thank the organizers for the invitation and the opportunity to share some of our work with you. So today, I want to tell you about our work on a hardware-based machine learning approach. We'll be touching on the foundational principles of implementing computation through the natural time evolution of a given physical system to process information. For instance, to classify images, or generally to classify time-dependent signals carrying information. So today's talk concerns physics of computation, computation with physical system, sprinkled with some ideas from quantum measurement theory. Though I'm going to be focusing on superconducting systems, the story is relevant to efforts in optical and AMO platforms as well, so do not be turned off by that. This talk is first and foremost geared towards the younger audience, the students, and to those young at heart. There's going to be a healthy amount of repetition, and I hope the experts will also find a few things that are interesting to them. So I encourage the students, please jump in and ask questions. That's important to me, if possible. So this work, so first, people behind this work, this work that I'm going to be touching on today is primarily carried out with my students Jerry Angelados, Fangjin Hu, and Said Khan. I'll also be touching only a bit on earlier work on the so-called T1 versus M bar problem in superconducting qubit readout that inspired this present work. You know, for those interested in that part, I'm not going to be talking so much about it. The results are in these two references. So that work has been done with my students, Moin Malek Aklak and Alexandru Petrescu. All right, let's see. Right, so here's the team, and here's Fangjin, Jerry, and Said. We can't go back to our offices yet, but we continue to carry out our work and have fun doing it together virtually. So I'm sure there are few in the audience here who is not intrigued by spectacular news coming out of quantum computing in recent years. It is clear things are getting a lot more interesting than, say, only 10 years ago. But more than what these machines are capable of in terms of real-world computing applications, these computing machines themselves are, for some of us, quite miraculous. This machine here, housing 50 qubit quantum computing chip from IBM, that is really a marvel of engineering like none other today. Very similar to what mechanical machines created by Leonardo da Vinci was in his time. They bring together major advances in microwave engineering, signal processing, refrigeration, digital computing, and generally physics, electrical engineering, and computer science that humanity has mastered in the past 100 years. So living at a time to see these machines up close and working with them is truly a privilege and awe-inspiring. It took some while for superconducting quantum circuits, that is the subject of the workhorse of today's talk, to transition from a platform for exclusively studying fundamental physics to a powerful technology for processing quantum information. Nonetheless, these complex systems continue, even more than before, to present a wonderful playground to study fundamental physics problems. Yeah. So just touching on a few things here that we are interested in the group. These, there are a number of very interesting problems in fundamental physics that we are interested in. As you know, quantum electrodynamics has been originally invented for fundamental particles like electrons in vacuum. And today, the quantum electrodynamics of solid-state systems like this, metallic dielectric structures, artificial atoms made of Josephson junctions, the quantum electrodynamics of those, they still contain a number of very interesting open problems that keeps us busy. On the other hand, these things are now, part of industrial efforts, and we have some interest in, for instance, computational electrodynamic modeling of these systems. How do you get from, just how this system is laid out in a metal to a quantum master equation that describes individual qubits here? Yeah? And so from that perspective, these essentially microwave photonic systems are really complex systems with which you can study nonlinear optics in the extreme. And lastly, these systems are, of course, of interest from computing perspective. And we have recently gotten interested in computing with dynamical systems, which is what I'm going to be focusing on. I'm showing here on the left an early example from Google that features 9 qubits. Nowadays, you have devices that contain 50 plus qubits, but this early example is nice because you can clearly discern the basic architecture. Today, these devices are accessible through the cloud interface, and you can write a piece of code, just shown here, piece of Python code, to carry out a certain algorithm you desire. For instance, a student connecting from Trabzon can just connect through the internet and essentially carry out a particular experiment on these interesting devices. A computation is essentially, I'm showing here in this case what's called a quantum approximate optimization algorithm, is essentially a known sequence of gates that is generally sort of laid out in circuit representation here. And the repetition of this sequence of gates on an identically prepared set of qubits thousands of times. Yeah, so you run this circuit with identically prepared qubits, in this case 3 qubits, thousands of times. The end result, the information that is used to implement a certain function or an algorithm, is based on the probability of occurrence of each bit string of ups and downs, or 0 and 1s, as you see here, for this 3-qubit device, you get, for instance, after a particular experimental run, this probability distribution of occurrence of these quantum qubit states. Now, of course, then this suggests that quantum computing is really different from classical computing as we know it, because it's intrinsically probabilistic computing, at least in view of the near-term algorithms that we are currently implementing. Okay, but what I want to emphasize for this talk is that computing is really all evolution of a multi-qubit system under the action of microwave and radio frequency drives, and subsequently the extraction of the system state through a procedure called readout, shown in this red block here. Readout is the most critical part of any computation you want to do with quantum hardware. It is important for initialization, important for feedback control, and feedback control is needed for a future error-corrected quantum computer. Yeah. So you want to carry out a readout procedure efficiently, accurately, and with as low latency as possible. So if you look under the hood, though, what appears to be a digital computation, in terms of spin ups and spin downs of individual qubits, is actually something more subtle. It takes a finite amount of time to measure a qubit to be up or down after executing a sequence of gates. And this is, I'm showing here like a bare bones description of what's inside. There's a lot more, but this is all we need for now. This readout is achieved by scattering a microwave pulse generated at room temperature through the quantum system one wants to measure, and passing the scattered signal through a chain, including a quantum limited amplifier and mixers and so on. This typically determination of a state subsequently, looking at the homodyne detector here, takes typically of the order of microseconds, typically. Okay. Then the signals are processed in a digital computer at room temperature that implements some type of filter to decide whether the given signal is from a spin that is up or down. Now here, it is important that much of the attention in the design of the architecture of these device, of this kind of a electronics and measurement chain is that that the devices in the measurement chain behave as much as possible as linear dynamical systems. Yeah, and that is important because you don't want to mix the signal and the noise in a way that you cannot separate later on. So while the processing in the digital computer at room temperature acts effectively for the for what we are going to talk about in this lecture as a nonlinear classifier. Yeah. In this talk, we will turn this upside down and replace the amplifier with another device that I will call the quantum reservoir computer. That does the nonlinear processing inside and allow ourselves to only use a trainable linear filter outside, at room temperature. And the motivation for doing so is related to an important problem readout that is known as the T1 versus M bar problem. Okay. So here's an overview of today's talk. The story that I will be sharing today has two parts. And I want to start by giving you a brief overview of the particular problem I'll be looking at. So you have a chart at hand to navigate when we get down to the weeds. The first part of the talk is on the physics of qubit readout. The speed at which one can accurately read out the state depends on the number of photons in the probe pulse. Yeah? And this, in turn, determines the signal-to-noise ratio. As you see, the two different blue and the red noise signals that essentially give us a signal for this, the qubit that is being measured is in the down or up state, right? You would like the signal-to-noise ratio to be as large as possible so that you can make this classification as early as possible, right? And a simple model, the linear discursive model on which the idea of quantum non-devolution measurement is based, would say, well, you can increase the signal-to-noise ratio by sending a pulse with a larger power. And you would expect something like this based on this model. But what happens, as predicted by a slightly more accurate model, is that the qubit now has a lot more complicated dynamics. And in particular, recent experiments have shown that for instance, the qubit relaxation time, T1, ends up depending strongly on the power of the pulse, in the pulse. And there's depending on, again, the type of qubit, the T1, so I'm referring to sort of the number of photons in the system by m bar induced by the pulse. T1 or the decay rate of this qubit, generally, the decay rate generally goes up with m bar, okay? And that's bad. Because this sort of puts you into a corner. You want to increase the signal-to-noise ratio. You want to send a larger pulse to read out faster. But then that readout pulse has a back action on the system you're trying to measure. And generally at high powers, things are a lot more complicated. This is something we have studied in earlier work, the physics of what happens, and found that really you need to start with a sufficiently accurate first principles model of the system. And a very good approach is to build effective quantum master equation models that is appropriate to the power level at which you're doing the experiment. This is a very general finding that turns out to be important. But here, in the second part of the talk, I will ask something different. I will ask, can one come up with a signal processing approach that is independent of the power level, independent of how complicated the dynamics, the system that is measured is undergoing, and independent of the model you describe it? Can one still do a good job reading out the state of the measured system? And one intriguing answer to that is an approach that is inspired by reservoir computing framework. Yeah? And very briefly, what we want to build is a superconducting preprocessor that does most of the job before the electronics at room temperature processes the signals. The idea of reservoir computing in this context is to feed in the raw signal coming from the quantum signal, something like that, that we want to measure, right? And inject it into a complex dynamical system to be specified later, which then evolves under the scattered microwave signals and maps the state of the quantum system that we are trying to measure into high-dimensional phase space of the reservoir computer. We will then ask, can then a trainable linear filter classify the state of the quantum system? Yeah. So This is a very different approach to computing. In this case, computing is a signal processing task with respect to von Neumann model computing in terms of hardware, at least. In fact, this hardware-based approach, as I will briefly mention later, is a very general way of thinking about computation. Okay, now let's get down to details. Qubit readout is fairly standard today and is practiced almost identically in all quantum computing efforts. It relies on the difference in the dispersive shift of the microwave pulse that is scattered through, or that is transmitted through a cavity that contains the qubit you're trying to measure. Yeah. And when this qubit is far detuned from the cavity resonance, what happens is that the qubit in the ground state and excited state act as slightly different resonance systems. As a result, the microwave probe pulse is getting a slightly different amplitude and phase shift depending on the state of the qubit. So one way to think about this is, the qubit is like a tiny dielectric material that you have inserted in your resonant cavity. And that dielectric cavity has a dielectric index that depends on the state of the qubit being either 0 state and 1 state, so that they they give rise to different resonances. And if you arrange that you pass the frequency right in between here, if you drive the system with a frequency that is right in between here, the state of the qubit 0, 1 is imprinted on the phase of the microwave field that is scattered. Okay, so I'm showing here how this looks like when the readout is optimized to death. Yeah, so this is data, recent data from Waldorf group from 2017-18, not that recent now. That shows, for instance, the observed microwave signal for a probe pulse in red here, when the qubit is in the ground state in blue here. Okay, it's noisy but not that noisy, and in the red up for the qubit up state. Okay, and but such optimization, and you can easily distinguish these signals now already at very early times, 50 to 100 nanoseconds right here, right? But in an online quantum chip, which needs to be periodically calibrated to offset slow drifts in qubit parameters and whatnot, this kind of optimized readout is often difficult to attain. Yeah. In practice, the raw signal looks more like this. The match filter. So what you have here is individual records here for qubit prepared in the ground state deterministically, that you can do with great precision, and in the excited state in blue shown here. You construct, to optimize this procedure, you must construct a matched filter from a large set of measurements. So you repeat this experiment thousands of times for each qubit state, get 1,000 different noisy signals. And if you average them, this gives you this red signal that, the evolution that's shown in this red line, solid line here. And for the qubits in the excited state, the blue line, yeah. And what it is essentially is match filter is this U, which is this noisy microwave signals, pass through a kernel that is constructed by averaging over many thousands of samples. And then you get a new signal, Y of t, which I'm showing here for red and blue, that, where you can draw a decision boundary, in this case here, so that when it falls on the upper side of this decision boundary, it's classified as qubit in the ground state. If it falls below, it's classified as the qubit up state. Now, this classification, you can easily see that it can be done faster if these two noisy signals, for instance, can be distinguished faster. That, according to the linear dispersive model, can be done by injecting a larger photon pulse into the system, larger M bar in terms of this parameter. And you see now the signal to noise ratio is pretty large, and the point at which we can distinguish the two states, is much earlier. This is different scales, by the way, up and in these two plots. Okay, but as discussed, what is actually happening does very much depend on the details of the experiment, the type of qubit, the frequencies, and so on. And generally, at least for transmon type qubits, the standard quantum computing variety, T1 turns out the intrinsic T1 time, relaxation time of the qubit is effective T1 time of the qubit is found to get shorter and shorter as you increase the power in the pulse for different M bars. So that's sort of you can appreciate this is a big problem, and there's been a lot of work to understand the physics of readout at high powers. And in recent work that I will not be able to get into, we found that really the right way or the effective way to think about the qubit dynamics in this case is really to come up with a parameterized effective quantum master equation that depends on the power level, on the excitation level in the system. But generally, this T1 sort of versus M bar problem is just one manifestation of what's happening. Generally, the system dynamics turns out to be a lot more complicated when you drive those systems strongly. And here you can see, you can understand in this calculation with a more precise model, which is still not as precise as it should be. You can already get a glimpse of what is causing this T1 shortening. Essentially, you see here two trajectories. The blue trajectory is supposed to be for the qubit in the excited state jumps early on to the lower state. On average, this is the average signal. For the two noisy samples, it's shown here, so they are no more distinguishable. You have essentially the qubit that started out in the excited state is now misclassified as ground state. Yeah. This is what is referred to as the readout error in the field. Well, you could say even if at high powers the qubit dynamics is complex and difficult to predict or calculate, and other mechanisms may come into play as well, such as crosstalk and so on, can one build a universal hardware-based approach that is model independent, is robust, and hardware efficient? That was our goal when we set out to start the work that I'm going to be discussing in the second part of my talk. We believe now, after the initial preliminary work, that a hardware-based reservoir computing approach presents such a potential. And I want to tell you about some results on that. So let me start with reservoir computing. It's a term that I've been mentioning freely until now, without really defining it. Reservoir computing is a deep learning framework for processing time-dependent data based on the idea of recurrent neural networks, but with a special training methodology. So for what I want to discuss here, you can think of a reservoir computer as a continuously evolving dynamical system, okay, with multiple nodes, that responds to an input stimulus UT and converts the input to an output stream, yeah, computing the function capital F of ut, which in turn is a functional of the output layer WO. And what is the output layer? Well, it's simply a linear sort of combination of the dynamical coordinates of this dynamical system to give you a new signal yt, which is the function f. Okay, so it's a linear output layer. That's what I will be referring to as a linear output layer. So reservoir computing is by now pretty well established, and the effectiveness of this approach has been demonstrated with various computational tasks, such as forecasting and classification, for a number of array of interesting information processing applications. And this idea has been in existence for the past 20 years. But today in my talk, I'm going to be discussing a hardware reservoir computing approach to processing quantum signals, okay, not classical signals. The reservoir computer that we envision is, in what we envision, a device made of Josephson nonlinear oscillators that reside in a cryogenic environment. The input signal to be processed is encoded in microwave signals that that encode a certain information, like image classification you want to do, and that is now impinges on your Josephson nonlinear oscillators, exciting the systems into an interesting dynamics, and scattering from those nodes off into another transmission line that routes it outside the fridge. And we want to train the output of this system, and one can consider various computational tasks. This is, as I indicated, it's subject for another talk. It's very interesting, very general information processing framework. And in this talk, the computational task we will consider will be the classification of the quantum signals coming from a quantum system you're trying to measure. And I will not be talking about some parallel work we are carrying out where we implemented image classification, classical machine learning task. Okay. So here's the proposal. In a typical setup, we envision the quantum system we want to measure is either housed in a separate fridge or the same fridge as shown upstream from the reservoir, superconducting, in this case, reservoir. And the quantum system is excited with the microwave pulse that is, as we have discussed, for readout is scatters of these systems. And that is injected. So this is sort of what you see here. The scattered signal is noisy, and it's sort of injected into the reservoir. That generates a complex dynamics, as shown here, which essentially integrates the signal, right, over its evolution in a complicated way because it's a nonlinear device. And then we want that for this particular task, we want to optimize the output layer, determine the WO, that is, that the quantum state of the system is classified with as high fidelity as possible. So once this is done, and if you have set things up correctly, the reservoir computer returns the real-time probability of the measured system being in a given state. So turns out, a single qubit readout is too simple for this kind of to evaluate the efficacy of reservoir computer approach. So we have turned to what's called joint dispersive readout of multiple qubits. And this idea of joint dispersive readout that we'll focus on here allows to measure the system of multiple qubits, I'm showing here 2, simultaneously through a shared resonator mode. So let's now assume that the system is described by a multi-qubit dispersive Hamiltonian, just for the sake of the slide. And it's not important that you understand what this is for the physics we are going to be discussing. And let me first go over the standard implementation of joint dispersive readout using optimal filters, match filters, as has been done in the Walraff group at ETH in 2009. Just like before, the system is initialized in known states with high certainty, okay? And for each state, thousands of pulses and thousands of runs are done. In this case, we have 4 states, right, for 2 qubits in the measurement basis. And for each state, you have 1,000 sort of samples, measurement records. And then you train your match filter, and that's not unique as we understand. So we don't actually know how Andreas Walraff's group has implemented this. This is all synthetic that we generate through our modeling of the system. And then, for, let's say, up, you get this match, the filter trajectory like this. And for each time you see, you have 4 bins now. And if this trajectory falls into a particular bin, you label it as such. Yeah. So this is already now, the job is done by the match filter optimization. Okay. Okay. So an important metric for readout calibration is classification fidelity, reached on a test sample at a given time as a function of the sample size Q. Yeah. So, as I said, you use certain number of measurement records for each state, known state, right, to construct this match filter. And if you use just one state, one measurement run for each state, so 4 measurement records, then the classification fidelity as a function of time of recording executes a trajectory like this. Yeah. And so what that means, for instance, at the peak fidelity, which is reached around 6 cavity lifetimes, you see 0.4, that means that only 40% of the trajectories are classified correctly. Okay. That's because you don't sample enough. So if you use 5 samples, you get this, 20 samples, 100 samples, and in the theoretical infinite number of sample limit, you still not get a finite peak fidelity, at a particular time here. And from there, it actually starts going down. And why does it go down? Well, basically, in this modeling, we model, and you have a lot of qubits that experience a back action and have a quantum jump, and you lose the information. So you cannot recover that information that is lost, right? So it goes down the longer you do this. Okay, now, so this is sort of as a function of Q, right? And what I want to do is now, do this for many Qs, also intervening Qs, and look at the peak classification fidelity reached. That happens. The peak classification fidelity is reached at different times for each sample size, right? And plot that value, that peak classification fidelity, as a training size, as a function of Q. Yeah, and you see how this slowly, as a function of the training size, the fidelity is reaching, saturating, and you really need, upwards of 100 trajectories here, and in realistic experiments, you would need, thousands of samples per state. Now we want to analyzing the rest of the talk how one can do this now with analog hardware based on the idea of reservoir computing that I described. And the chief goal is going to be to reduce latency without compromising classification fidelity. So before discussing the training procedure and performance, a few words about the physical structure of the reservoir. We envision we have a reservoir that is based on Josephson junction nonlinear oscillators, where exchange interactions are mediated by a common electromagnetic environment. Yeah, and this kind of and that is described by this Hamiltonian here. You got the individual nonlinear oscillators. Their nonlinearity is shown here in lambda, capital lambda. That will be important. They're hopping between the nonlinear nodes. And finally, this is what I call the input layer at Hamiltonian level. This is where the information comes in and drives these individual nodes. And to construct the data that I've shown you, we essentially need to solve the quantum master equation. I think what I'm not showing here is that the important piece is that we're actually solving the stochastic quantum master equation so that we can sample individual trajectories that one would be getting at room temperature, right? Oh, so one detail is that the results that we are going to be discussing in the rest of the talk is going to be in the semi-classical limit, where the signal to noise ratio is very high. So we'll be driving the measured system with very high intensity with large pulses. And so that sort of makes the computational work feasible, because we'll be also basically looking at a large system here. Okay. So yeah, and yeah, another important aspect probably I should mention is that the parameters here. For the nice thing about this reservoir computing approach is that the parameters here don't need to be fine-tuned. They can be all within a certain range of parameters, and that's a very important. Turns out to be very important. So finally, some results. I'm showing here a visualization of how training looks like for a 5-node reservoir. We have chosen the parameters to be within the range of fabrication capabilities. Here is one trajectory, noisy trajectory, for one of the quadratures of the microwave signal that is sort of coming from a system containing a qubit that is prepared in the up state, that deterministically prepared up state, right? And we inject it into the reservoir. Here is the evolution of the individual nodes of the reservoir, undergoing rather complex nonlinear dynamics. And I'm showing here now, this is now the output layer has been optimized through training. And I'm showing now here a test situation where I'm plotting the evolving probability distribution that the system predicts for this particular noisy input. And you see over a certain time, the probability of the reservoir predicts the probability of finding the state in up state saturates over time. Now, I want to show you also the ground truth for this, right? Which is we have access to because we are simulating this. I'm showing here in the dashed line for this particular up state how its probability is varying over time. And you see here, this qubit experiences some, quantum jump-like fluctuations. And despite that, the classification fidelity probability remains high. So this, this tells you really that these reservoirs are very effective in classifying these states. Well, details aside, there's a lot of detail that I'm not going to be able to discuss here. But the most striking result of this work and the takeaway message is that the reservoir computer is a fast learner. Okay? After already seeing just a few samples, the reservoir, few samples per state, the reservoir is able to classify with rather high fidelity. I'm plotting here the same plot that I had for the match filter. Pre-classification fidelity is a function of the training sample size. And as you see, it's already starts very large and remains high. And so, and I remind you, this is not a huge reservoir as typically is used in classical reservoir computing literature, where typically you simulate a 1,000-node reservoir. This is a 5-node reservoir, and it's able to really do this quite efficiently. Okay, it's when we basically ended up sort of getting, when the dust settled, and we saw that this is where a reservoir computer is very effective. It can learn very fast. And that is very important for online quantum computing systems, where these systems have to be periodically taken offline to be recalibrated, the readout system calibration and all that, simply because there are essentially random qubit drifts and so on. This offers a really important prospect for doing that calibration very fast. Okay, so of course, as physicists, we were intrigued why such a small reservoir is able to do this classification task. And in the last two slides, I want to show that you can actually get behind this. I'm showing here a cut through the measurement space of what we are recording, what is coming from the reservoir. Yeah. So normally you would record 2 quadratures per node. Okay. So if there are n reservoir nodes, there would be 2n dimensional phase space in which the dynamics is taking place in response to an incoming microwave signal. And we were able to bring it down to just 2 nodes and still be able to do where we can actually visualize what is happening. So this is 2 nodes, and we are taking a measurement surface of section through this 4-dimensional phase space of 2 nodes. And here are the results for thousands of measurements with upspin, up, and this is thousands of recorded signals in the steady state when the reservoir reaches steady state for 0, 0, and so on. And this is when you classify, when you construct the optimal sort of output layer. What you're saying is that you can draw these lines that pass through the origin that can or cannot separate these distributions. In this case, we managed to do that. Yeah, and each of them lies in a different place, each of the distributions, and therefore anything that lands here we classify as qubit. What is this? So unfortunately, my color blindness is causing difficulty here, but I think this is 0, 0. Yeah, down spin. But why is it that that my reservoir, by just looking at single trajectory, actually do this classification? You know, that's the thing. That was the key finding. And I'm showing here individual samples, individual trajectories for the evolution of the reservoir. Now, these are, you know, many sort of averages in the steady state, but now I'm showing you individual trajectories. And you see that individual trajectories pass right through this distribution, right? And right here. So that is why, because individual reservoir trajectories are information rich, and they sample the phase space as many measurements would do for you. Okay. And that is not all. You can show further that nonlinearity is essential. You know, you could say, well, what if I use a linear reservoir? Yeah, and that's shown here. For a linear reservoir, nonlinearity is 0. You will find that these distributions sort of fall almost on a line. Okay, and so according to this linear classification scheme, they cannot be separated. You know, if you look at it closely, you will find that only 50% of the trajectories are classified correctly. The high accuracy of the nonlinear system is really due to its nonlinearity, which works by essentially tilting these distributions in the phase space so that they can be linearly separated. Right, so this really brings me to the end of my talk. Thank you for listening patiently. I want to give you some take-home messages in this last slide. I told you that reservoir computing approach, told you about a particular approach inspired by reservoir computing to quantum signal processing. And I've discussed a proposal for a hardware-efficient cryogenic analog processor for readout. And I've shown you that really, most importantly, the lesson we learn is that such a reservoir has a fast learning capacity. And what I've not discussed is that, you know, readout is the simplest thing you can do. It's a basic building block of many more complicated things like quantum state tomography. And finally, this scheme is really general, fairly general. You know, it can be done in optical range regime, and you can apply it to various quantum systems and different measurement schemes. Thank you.
So I'm applauding on behalf of everybody. Thank you very much, Hakan. This is a very inspiring, very modern, very fresh and nice talk. So I will look to the audience for some questions. I will also have some of my questions as well. Okay, so let's start with the question from Professor Zafer Gedik of Sabancı University. He asks, should the reservoir computer obey the second law of thermodynamics? Can decreasing entropy be an advantage?
So, you know, I do remember my thermodynamics class from Zafer. So, you know, and looking back, I think I had a hard time understanding entropy. And now I understand why. And that is because, you know, everything we do here is really in full non-equilibrium. And the classification here is done in the transient, right? I mean, we don't even reach steady state. Where you can think of an effective equilibrium. But I think I understand what Zafer is getting to. And that is, you know, what happens, perhaps, if I understand correctly, when you get to a situation where the excitations are is much at much lower level, and that happens when you drive the readout cavity with a very weak signal. You send one photon, let's say, through the readout cavity, and then the reservoir computer operates totally in the quantum regime. You have to, and what happens at that point is really the subject of the most exciting part of the study. That's where we wanted to get to. What happens in the quantum limit? The results I'm discussing are, taking into account quantum physics to a certain extent, but the full quantum limit, where everything is sort of talking to each other, and you get lots of fluctuations and noise far larger than the signal. I don't know how it would help. I don't know how entanglement would help, because we clearly see that entanglement is not, is not the starting point here, right? If we do find it here, that entanglement is important in the reservoir, then I will understand how entanglement is important for quantum information processing, finally. I hope that's the question he asked. At least that's what, what I understood.
Thank you. So there is another question, maybe somewhat related to this, by Emre Taşkın. Dr. Emre Taşkın is from Hacettepe University. He wants to know about the implementation. When you send the single pulse, do you know which one it will interact, which qubit it will interact with? And do you expect some kind of coherent superpositions of these qubits?
Yeah. Well, so that's the input layer, which I didn't touch on. So, in this setup, you will find essentially we have a time series, right, for a signal. It's a scalar signal. And this input layer is supposed to distribute that signal with different weights into the individual reservoir computers. So all of them see different, weighted sort of versions of the the stochastic input signal. And of course, any kind of superposition state or entangled state generated in the reservoir is going to be important. But as I discussed in this talk, the results I've shown you and that are currently in the is public in the public domain in this paper that I've shown initially. That's done in the semi-classical regime. Very high power, lots of excitation in the system.
Thank you. So Emre wants to continue asking somewhat related to that. So if the initial state is not like up and down, but also some superposition like 1, 1 plus 0, 0, can you still classify it, or?
Yeah, that's exactly, we have looked at that question. So once you train it with the basis states, right, you train it with you allow yourself to only train it with basis states, it is able to discern the probability distribution of a superposition state of, let's say, 0, 0, and 1, 1. But the probability distribution. So it wouldn't, in a sense, if you go with the current scheme and come up with something creative, don't come up with something creative, it wouldn't be able to distinguish whether that's in a mixed state or whether it's in a coherent superposition states.
I see. So let me take this break and ask my question. So the learning process is about finding some weight factors typically to these connectivities, but there is also this so-called morphologic or neuromorphologic computation approaches where these reservoir connectivities are also important. And there are some models which connectivity will give the best. So is there also some kind of optimization here regarding the connectivities, or?
Yes. So let me just, touch on one thing. This is essentially what, very broadly, what folks call in the community, one talks about neuromorphic computing. This is one instance of that. But it's distinguished by the fact that you do not train the internal connections. Yeah. So it's given by the design, and you only allow yourself to train this output, linear output classifier, linear classified at the output. So that's one. Two, there's been some findings in the reservoir computing community that and that's for classical dynamical systems, that the classical dynamical system has to be at the edge of chaos. And that, and then there's some related understanding of what kind of interconnection matrix WR puts you there. And then you can relate it to some singular values of that connectivity matrix. But we studied this as part of this work, and what we find is slightly different. And probably that's maybe subject of another research talk on this topic. It's very interesting.
Very interesting. It has some kind of connection to all these dissipative phase transitions and other
Say again?
Dissipative phase transitions and other things, the chaos and fluctuations. It's very interesting when you bring this many-body reservoir in.
Right, exactly. I mean, this is sort of, for theorists who's close to applications like me, these systems really represent tremendously interesting systems because they are what we would refer to as complex dynamical systems.
In this regard, Hakan, let me also ask you, maybe you can speculate, if you also do not only readout, but state preparation with using reservoirs, and in middle also computation, so some big universal wholly reservoir, full reservoir computation picture, is it something that you want to go in future, or do you think this is a promising direction? Yeah,
absolutely. I mean, this is, we are very engaged and interested in exactly towards that goal, where this is for a specific application. You I think touched on the right point. This is for just readout, classification of quantum signals, but it's the real power of reservoir computer resides in additionally feedback. And when you get there and think about feedback, this whole thing becomes just a computer on its own. So where we want to get to is really think about generally computing with dynamical systems like this. Yeah.
Perfect. So I don't want to be taking time from other audience. So there is another question that I want to read. It's a little bit long, so let me read from Fatih.
Yeah, sure.
Why are we training only a single readout node from which we do time-dependent trajectory classification? Is it due to historical reasons? Isn't it training to do n separate classification readout nodes more convenient, both in terms of robustness to noise and in terms of scalability to larger number of qubits? I ask this because the trajectories will be very narrowly separated in the output time series as we increase the n beyond 2. Well, maybe Fatih, you can also, maybe, I don't know if our moderators can do it. Maybe you can turn on and unmute yourself.
Honestly,
you can discuss, because it's a long question.
Towards the end of the sentence, I forgot the beginning of it.
Yeah. And we kindly.
Yeah. Why doesn't Fatih come online and ask me directly?
It will be easier.
Thank you so much for the talk. It was really fun and fruitful for me, and I'm pretty sure for many others as well. Yeah, I couldn't ask because I was muted and I couldn't unmute. So the question is the following. I might be misunderstanding as well, but I see that you are training a single readout neuron from the reservoir that basically does some sort of like a regression, and then from the regressed output trajectory, you are doing a second classification based on where the trajectory is in terms of time. Wouldn't it be easier to train like multi-neurons, all of them are still linear, but instead of doing a regression, so like instead of doing a trajectory regression, you would do like a classification, and then those would tell you basically whether, like, if you have like 2 different qubits, then you would have 4 output neurons, and then each of them would pop up whenever like the initial condition is one of them, right? That would be easier to train, and it would be scalable because once you have many qubits, then the neural trajectories of the single dot would be very narrow and non-robust to noise. If that makes sense.
Absolutely. Very good point. In fact, I mean, in other work, related work, that's what we do, with one difference, if I, didn't misunderstand you. So we know, the right thing to do, especially if you have multiple classes, is to have an output layer which is multidimensional. And so then WO becomes a matrix. And we train, essentially all the neurons then at the output. So if I understand you correctly, because, for me, these reservoir nodes themselves are neurons as well. But the distinction here is that we do not do any thresholding on the output nodes. So and I understand what you're saying, and one would have to look at the efficacy of this approach compared to a linear classifier here. But you can still use the same number of neurons at the output, do it linearly and non-linearly with nonlinear thresholding, and see how good a result you can get and compare. Does that make sense, or were you trying to get to something else?
Fatih?
Sorry.
Yeah, please go ahead.
Can you hear me?
Yes, we can.
Yeah.
Now.
It does. I might have misunderstood something during the talk, so I will probably reach out later on.
Please do. Yeah, I'd appreciate it.
Yeah.
Thank you. And I can't see any more questions except one nice question from Devrim Tarhan. It's also some general question that maybe it's a good question to complete the session. So Devrim wants to know, suppose we learned these methods of machine learning, reservoir computing. Is it applicable beyond these superconducting systems? Is it applicable to some other differential equations? How general is it?
Oh, when we started learning about this, it's new to us as well. I would say we started thinking about this about 2 years ago. And in the meantime, to me, this is as general as computing with physical systems get. Really, reservoir computing gives you a very general physics of a computational machine. Essentially, everything we do in signal processing, everything we do in image processing fits into this framework. The only thing is we don't worry about this being digital. It's an analog thing, and we don't worry about this machine being constructed to precise specifications. We put all the burden on the training of the output layer. So in that sense, it's very general, it's very practical. And in terms of what physical systems, I can tell you that this is, become so ridiculous that people have done computation with a bucket of water as well, which I tend to show in other talks, for fun. So take a bucket of water, make the bucket shallow, water shallow. That water is governed by shallow water nonlinear wave evolution equations, sufficiently complex and nonlinear, and you train a optical sort of mask to train it to read out the right result for spoken digit recognition that is acoustically modulated into the bucket of water. It works. Beside one, I think a big question in the field today is, why does it work? How can we generalize it? And if you push it to the quantum regime, what do we have to pay attention to? And
Thank you, Hakan. So the young people, you get your message. Go ahead, read Hakan's papers and more, and think about it. Imagination is always the limit. So I applaud Hakan again for this very nice talk and being with us.
Thank you.
And for this nice evening shared with Hakan. Thank you very much for our participants, questions, and everybody talk today. And thank organizers again.
Okay. Good evening to everyone.
Good evening.